Hello, this is Ian McDonald, and this is my AP Physics 1 first semester project that I'll be doing on biomedical engineering. To start off, this is just a basic overview of what you'll be seeing in this presentation. I'll begin with showing common car crash injuries and how they happen. Then I'll explain the relationship to Newton's laws, and finally I'll wrap it up by tying in car crash data analysis of a head's acceleration. The first type of collision I'll be talking about is a rear-end collision. One of the most prevalent injuries in a rear-ended collision is whiplash. And whiplash is basically the violent acceleration and deceleration backward and forward of the head and neck. And since the thoracic and lumbar spine are attached to the rest of the car, or at least protected by it, the head and neck are left vulnerable and they're kind of floating. So without a properly set headrest, the neck wants to stay in the same place and wraps around the seat backward while the car moves forward. And the neck is then violently thrown forward once the car stops, damaging the soft tissue in the neck. So after whiplash, your head can be thrown violently forward and hit a hard object like a steering wheel, causing trauma. And this can include a concussion, where your brain hits your skull and damages it directly. And this is actually especially prevalent among teens. Car crashes are the leading cause of traumatic brain injury-related deaths among 15 to 19-year-olds. To tie all of this together, we have to remember that a body in motion wants to stay in motion unless acted upon by an outside unbalanced force. Since the body is directly attached to the car, it travels at the same velocity as the car at which it was hit. The head wants to stay at its original velocity because it is not directly attached to the car and has a delayed reaction with the body. Because of inertia, the head does not experience a strong enough outside force to change its original velocity, causing whiplash and concussions. We can use Newton's second law to figure out the force of the head. The unbalanced force equals mass times acceleration. Multiply the mass of the head, usually 5 kilograms, by the acceleration, which is Earth's gravity, 9.81 kilograms per Newton, times the amount of g-force the head experiences. I'll be talking about front-end collisions next. The lower body is subject to injury from front-end collisions because it's usually the first part to hit the car first. Sometimes the knee will hit a steering wheel, tearing an ACL, or the sheer force of the airbag can dislocate a hip. Chest trauma is another injury that can happen. Sometimes the seatbelt restraint can break a breastbone or a rib. Internal organs can be lacerated from the sheer force of the airbag slamming into one's torso. To tie in Newton's laws, picture a convertible with a man driving with no seatbelt hitting a wall. The wall acts as the outside unbalanced force and stops the car while the body unhinged continues to travel at the car's initial velocity and is launched out of the car. The person wants to stay in motion because the outside force only affected the car. Because this person was not wearing a seatbelt and was driving a convertible, no outside force changed its original velocity when they were in the car. The force of the car on the wall can be calculated using Newton's second law. The mass of the car times the acceleration, which is gravity times the g-force, will equal the force of the car on the wall. The next thing I'll be talking about is side impact collisions. T-bone collisions can be some of the most dangerous car accidents, especially when the driver of the impacted car is hit directly. The spine is most vulnerable in this case, oftentimes resulting in herniated disc or spondylolisthesis, which is a disc slipping out of place onto the bone below it. In crashes between passenger cars, 51% of deaths occurred in side impact accidents. Adding SUVs and trucks into the mix increases the rate to 60%. T-bone collisions can also result in injuries from the windshield. These can lead to lacerations across the skin and punctured organs. This can be especially deadly when the side impact collision is so strong that the car rolls over and the body is subject to broken glass from all angles. Newton's third law states that for every action there is an equal and opposite reaction. For example, if a smart car T-bones a large Jeep Wrangler while both are traveling at the same velocity, both vehicles experience the same amount of force, but in opposite directions. The force of the smart car on the Jeep and the force of the Jeep on the smart car are found in separate force diagrams and are a Newton's third law pair. Since the smart car has less mass, it would have greater acceleration than the Jeep, causing more damage on the smart car. Once again, the force of the Jeep on the smart car can be calculated using Newton's second law. Mass of the Jeep times acceleration, which is 9.81 times the amount of G-force. Here is crash data measuring the acceleration on a head during a car crash. The head's acceleration is measured in G's and is the dependent variable, while time is measured in milliseconds and is the independent variable. At its peak, the head accelerates at around 33 G's for an instant. 1 G is equal to the force of acceleration from Earth's gravity. At the bottom of a roller coaster, a person can experience 5 G's. Now multiply that 6 times over. Injuries like concussions and whiplash only make sense in this perspective. The head wants to stay at constant velocity, as the car was most likely traveling at a constant velocity at 0 seconds. But since an unbalanced force acts upon it, it accelerates, even if it's for 400 milliseconds.